also on the same left side. So stick as it is. You're not going to flip it. You're not going to change the direction of the arrow. So it's going to be the same as it is. Let's see. You need you need hydrogen gas. While you have hydrogen gas over here in direction number 3, the only difference between number 3 and the desired equation, which is equation number 4, is that the amount of hydrogen. The amount of hydrogen you need is 3, so you're going to put 3 in front of that hydrogen. So you're going to multiply the whole equation by 3, and this becomes 3. And the heat of reaction also need to be multiplied by 3. Okay, go back to the 2 carbon just now. You have 2 carbon, so you need to multiply by 2. That's 2 oxygen, 2 carbon dioxide, and multiply the heat of reaction 2 by 2. Okay, so everything needs to be multiplied by 2. So your third component in the reaction number 4 is your ethane. I'm assuming that is ethane. So your ethane is on the right hand side of the equation, but for reaction number 1, your ethane is on the left hand side. So we're going to flip that first equation so that it will be on the right hand side. So we're going to rewrite the equation. We're going to rewrite it so that it will be on the right hand side. You don't need to change multiply it with another value, because the coefficient in front of ethane is the same as the one given in equation number 1, so it's the same, so you don't need to multiply it with a value. This is the equation. So you have to do the same thing with the heat of reaction for that reaction number 1. Instead of having a negative, now since you flip it, you're going to have another negative in front of that negative value. This is from equation number 1. For reaction number 1. And now that become this equation now become that equation because we flip it. So we're going to ignore this equation. So we have equation number, not equation, I keep on saying equation, reaction 1, reaction 2, reaction 3. We're going to add it up and make sure that we end up with our desired reaction number 4. So let's have a look. Unfortunately, I cannot do it immediately under this equation. So let's see. We have 2 carbon on the right hand side, which is the same as the desired equation. You have 2 oxygen. Do you have 2 oxygen? Yes. Do you have it? No. You need to not oxygen. You need to come up with, let's see, add up equation, reaction number 1 with number 2. This is 2 oxygen. You have 3/2. Let me highlight it so that so that you can see what I'm pointing to. That's 2 oxygen. That's 3/2 oxygen. Any more oxygen you have over here? 7/2 oxygen. Okay. That's 5/2. Where's the other 2 more oxygen? Nobody?
Doctor, it's 4/2 plus 3/2, which will equal to 7/2.
Okay, thank you very much. It should be 3/2, and that is 4. Hold on. Which reaction are you referring to? Number 1, number 2, or number 3?
Number 1 is 4/2, which means 2.
Oh, let me erase this. Is that over 2? Look, I multiply it by 2. I also multiply this by 2. That's correct? Isn't it?
Yes.
Okay. This one, 3. I multiply by 3. 3 hydrogen. So how come I got, if I multiply by 3, it should be 3/2 also, isn't it?
I mean, when you add it, we'll have 2 in the 2 down and 4 up for the first equation. Because it's 2/1. We want it to be over 2.
The first equation, the first reaction.
Yes.
You are referring to this equation, this one.
Mm-hmm.
Okay. You multiply by 2, everything by 2. So why is it that I got it wrong? Let me see. This is oxygen. Initially, it was like this. Okay. Then I multiply it by 2. That's 2 carbon, 2 oxygen, 2 carbon dioxide, right? isn't it? Somebody, please check. So now that's 2. Now I multiply by 3 because I have 3 over there. I multiply the second equation by 3. So that's 3 here. Now this part, if I multiply by 3, what change? What happened? 3 over 2, isn't it? So it be 6 over 2. Should it be 3 over 2?
Yes.
Yeah. So that it should be 3 over 2. If I multiply by 3, it becomes 3 over 2. So it becomes, oh, sorry. I can see what you mean. This is 4 over 2. This is 4 over 2. I can see what you mean. Okay. Thank you very much. I have problem with my mental arithmetic. Okay, this turned out to be 4 over 2, isn't it? Okay, let me undo that. So I'm going to write it as 4 over 2. Isn't that right? 4 over 2 is the same as 2. Okay, and this one is now 3 over 2. 3 over 2 plus 4 over 2 come up with 7 over 2, isn't it? Guys? So you cancel that, you cancel that. Okay, now you get rid of your oxygen. Oxygen. You get rid of your oxygen. Now, what else do we have that we can get rid of, that we can take out of? Okay, water. You have carbon dioxide on the left hand side, carbon dioxide on the right hand side. So you end up with, you bring down from the first equation 2C, from the first reaction. From the second reaction, you have 3 hydrogen. You have no more on the left hand side. Now go to the right hand side. There's no, from the first reaction, there's no term on the right side. From the second reaction, there's no term on the right hand side. From the third reaction, there is your ethane. So that finally you get what you wanted. That is your desired equation. So now what we have to do is we sum up the heat of the reaction. You have minus 393.5 times by 2 plus 3 multiplied with that value of 285. There's a negative there. And minus, actually plus or minus doesn't matter because minus times by minus become plus 1559.8. So finally, what will you get the same value as this after you have done the mathematical calculation, after you have done it, calculating the value? Is it minus 84.6?
Yes, Darshan.
Thank you. Good. Very much. Thank you very much. So it's the same. The answer is the same as the solution given. Yeah, so that's how you play around with your chemical reactions. With the heat of reaction, you do it as if it's a mathematical problem. You multiply it, you change it, you flip it through. That's what you have to do in order to get your heat of reaction. Okay. The heat of reaction we have mentioned last time. The heat of reaction is the heat that is either endothermic or exothermic, depending on the reaction. If it's exothermic, you have the negative sign. If it's endothermic, your heat of reaction will be positive. What happens is that during the reaction itself, these are the heat that will be released or that you have to supply in order for the reaction to occur. So that is what the heat of reaction is all about. And you can calculate your heat of reaction using 2 methods. I've mentioned that before. You have the heat of formation, which you can get from your appendix B1. Okay, so let me highlight this. This is your appendix B1. You have 2 methods of getting your heat of reaction. The first method is that you use your heat of formation. That is your heat of formation. The subscript, the heat of formation is written as such. Okay, that's F formation. The superscript 0 implies that it is a standard heat of formation whereby it is at 25 degrees C and 1 atm. Okay? There's another method that you can use to get your heat of reaction, which is the heat of combustion, and it is written as the H with a cap on it, your superscript 0 and a C. That C is the subscript C implies that it is for combustion. Again, the superscript is for 25 degrees C, 1 atm, the standard value, standard temperature and pressure. But that is not STP, the one that we have discussed before. Do not get confused with STP. Okay, this is for formation and combustion only, for reaction. Okay, so you can get this value from your appendix B1. So let's have a look at just now that example that we just covered just now. Let me erase so that we can have a good view of everything. That's the good thing of having teaching online. You can erase it and then you can also undo it. Okay, let's have a look. This is heat of formation. Heat of formation is about creating your component from its natural elements. These are natural elements. That means your elements are the ones that are occurring naturally. Oxygen is always in a gas phase. There's no way you can get oxygen in a liquid phase. Okay, that is how oxygen occurs naturally. So this is your oxygen, and this is your carbon. Carbon is a solid. You will form your carbon dioxide from carbon solid and reacting it with oxygen. So this is your heat of formation. This is your heat of formation. Even though it is written as with that subscript of R, implying that it is reaction, but actually this is your heat of formation because the reaction itself is a reaction process. So if let's have a look, I'm not sure whether my table here has carbon dioxide. Okay, carbon dioxide, no, the last component is carbon. All right, so let's have a look at that value in our appendix B1. Let's go to appendix B1. Okay, so this is appendix B1. And if you scroll up, the carbon dioxide is here. That's the carbon dioxide. And your heat of formation, there's two heat of formation. Either it's liquid or gas. And the one that we are looking at is the gas phase, which is negative 393.5. Let's have a look at that value. Negative 393.5, whether that is the same as the one written in this example. Yes, guys, that is it, negative 393.5. So you get that value actually from table B1, and it is actually your heat of formation. Why is it written as heat of reaction? Because it is referring to this reaction. It is referring to that reaction. Okay, now let's see whether there's any more heat of reaction here. Okay, we have this being formed. Oops. We have water being formed from hydrogen gas and oxygen gas. Your elements, the elements in this natural state is hydrogen and oxygen. These are the elements that occur naturally. And the compound that is being formed is water. So this is your water being formed. So this is again your heat of formation. And you will be able to get that value, which is this value from the appendix. Again, take note, what is this phase? Is it gas or is it liquid? It's not written here. Is it gas? Oops. Is it gas or is it liquid? We don't know. But let's look at this value, then we will know. Okay, it's negative 285.8. So let's go back to our appendix B1, and we'll be looking for water. So it will be the last few components in the list. Okay, that's water. So this is water. And just like I mentioned just now, you have liquid or gas. So which is the one that is referred to in that example just now? Is it liquid or is it gas? Guys? Anybody?
Liquid, doctor.
Liquid, because that's the value given. Negative 885.84. That's the value given. So that should be liquid. It should be written in the equation. They cannot just leave it out. It should be written this as liquid. Your water is liquid. It makes a lot of difference because there is two different values when liquid water is being formed or water vapor is being formed. It's the values of the heat of formation, they are not the same. So it's very important that you list it down as liquid or vapor. Okay, it should be written down. Okay, the others, this is for this equation. Let me highlight it. Okay, for that equation, for the one for ethane, is it a heat of formation? Is it a reaction formation? Is the reaction formation reaction? For the first reaction here that I just highlighted, is this a formation reaction?
No, doctor.
No, nothing is being formed here because you are not forming carbon dioxide. You're not forming water, so it's not a reaction process. Reaction. It's not a formation reaction. Sorry, it's not a formation. So this is not a reformation. The only two reaction that is formation is these two. So now let's have a look again at more examples. Okay, before looking at example, the definition of heat of formation. Heat of formation is when you form 1 mole. Your product must be 1 mole. Do not put 2 mole, do not put 3 mole. It should be 1 mole of your product or your compound from the elements that occur naturally at a reference temperature, usually 25 and 180 M. That is the definition of heat of formation. So the standard heat of formation, again, that superscript implies that it is at 25 and 180 M. That's the standard heat of formation. So for sulfur trioxide, we have that value. I hope it should be kilojoules per mole there. Per mole of what? Per mole of sulfur trioxide. Okay. And for your ammonia, this is the heat of formation, which you can get from Appendix B1. And another thing that you need to know, okay, we are looking at the element. If you're going to form, for example, oxygen, oxygen is already occurring naturally in its natural elemental state that is occurring as a gas. So when you want to find the heat of formation for oxygen gas, the heat of formation should be 0 because you cannot form it from any other element. It's already in its elemental form. You cannot form it from any other sources. It's already occurring in its elemental form. So the heat of formation for oxygen is 0. Another example, hydrogen gas. The heat of formation of hydrogen gas is also 0. So let's check whether what I'm saying is true. Let's look at oxygen. Whether your heat of formation is 0 for oxygen. MnO. Oh, it's here. Okay. Where is our oxygen? Okay, there is our oxygen. Let's go horizontally. There is your heat of formation. It's 0. Okay. So just now I mentioned about hydrogen. So let's look at hydrogen. There is our hydrogen. That's hydrogen. And your heat of formation is 0. Okay. So when it is already in its elemental form, the heat of formation should be 0. Unless it's a compound. If it is a compound, you need to form it from its element, then there will be a value for the heat of formation, which is given in this table, or you can find it from other sources. It's not there in Appendix B1. Okay. So I already mentioned about this table. Okay, now let's scroll up. This is one example where you can get your heat of formation for ammonium nitrate. Let's have a look at this. There's 2 values here. C implies that it is for solid. Aqueous implies that it is mixed with water. Okay, so there's a difference. So for this case, it is solid. So you'll be looking at the first value, the heat of formation. Let's look at more. Okay, now, how to get the heat of reaction when you have the heat of formation available? Your heat of formation you can get from Appendix B1. You wanted to find the heat of reaction. You wanted to get the heat of reaction from the heat of formation. So this is the equation that you will use. You have another method how to get the heat of reaction. You have two methods in order to get the heat of reaction. You're going to get, for example, in this case, the heat of reaction of this reaction. You're going to find that in fact, you have three methods, not two, three methods. The first method we already discussed last week using His law. If you have a few reactions given with the corresponding heat of reaction, you can play around with it mathematically. You will end up with the desired reaction that you want using His law. That's the first method. The second method is using the heat of formation. So you will get your reaction from appendix B1. You will write the reaction based on the formation of that compound and get the heat of the formation from appendix B1. And then after that, you do it using His law, and you will get, you don't even need to use His law, sorry. You can use this equation. You can use that equation without going through His law. But if you want to use His law, you double check whether your reaction is correct, whether it come out to the desired reaction that you want. Okay, so we will play around with it. That's the second method. The third method is from the heat of combustion. You also get your heat of combustion from appendix B1. You write the equation, and then you play around with it using His law, and you end up with the desired reaction that you want. But if you don't want to play around with His law, you can use the equation for heat of combustion. We will look at that later on. Okay, now I will scroll up. I will skip a few steps first because I want to point out something to you guys. I will point out both the heat of combustion and heat of formation. Okay, how to get the heat of reaction? I highlight it. This is your heat of reaction. This is your heat of reaction. You have two methods. Just now I mentioned three. This is two methods. The other one is his reaction. His law. Is it his law? Is it his rule? His HESS. His method. Okay. So now for heat of formation, this is the equation. For heat of combustion, you have the other equation. The first equation is for the heat of formation. The second equation is for the heat of combustion. The difference between the two is that the first, this is product, this is product. Okay? Your reactant is over here, your reactant is over here. How to remember? When you're looking at heat of formation, you form product. You form product. So the first one should be product. When you look at heat of combustion, you'll be burning or combusting the reactant. You'll be burning or reacting the reactant. So the first term will be your reactant. That's how you remember. This is, if you don't want to remember, it doesn't matter because it's open textbook. But then if you remember, it will be faster for you to, you know what to do. Yeah, your heat of reaction, when you're using heat of formation, the first sigma will be product. If you're using heat of combustion, the first sigma will be reactant because you'll be reacting that fuel, you'll be burning that fuel in order to get your reaction. If you're using the heat of formation, you'll be forming your product. So that's the first sigma will be product. Okay, so let's go back to the heat of formation just now. Okay, that's the equation. So I just pointed out to you guys, this is your product, this is your reactant. Again, remember that this is the coefficient, the number in front of your chemical. That is your coefficient. So let's have a look at this. The coefficient here is 1. The coefficient here is 8. The coefficient here is 5. And that is 6. That's the coefficient. So if you use that equation, your heat of reaction is equal to sigma. Your product is formed. Your coefficient is the number in front of the chemical, and your heat of formation. Minus your reactant, your coefficient, and the heat of of formation. I'm repeating the same equation over here. Yeah. If you rewrite it, this is more or less what you will come up with. That's the reactor. Sorry, the product. I'm going to erase this. I'm going to erase this because it's the same thing as the one listed there. That's your reactant. Sorry, product. That's your product. These are your products. And your reactant, these are your reactant. So you should be able to get these values from the appendix, the heat of formation. But the heat of formation of oxygen is not listed here because the heat of formation of oxygen, as I mentioned earlier, for oxygen is equal to 0. So you don't need to write it there. So automatically the heat of formation of oxygen is 0, so you don't have to write it there. So you only have these three components that you will substitute inside this equation. You end up with your final heat of reaction. So that will be your heat of reaction for that reaction. Well, explaining it in this method is not going to help much, so let's do an example. This is your desired or your reaction, the reaction that you're interested in. You wanted to find its heat of reaction. You are given the heat of formation for these three reactions. Yeah. As always, hydrogen, it should be 0 because it is already existing in its elemental form. Yeah, so you don't need to write actually for hydrogen. You can skip that step. You only have the first reaction and the third reaction that you need to know, the heat of formation. So now, if you're going to use this equation, so let's do it over here instead of looking at the answer. We have your heat of reaction. I'm going to rewrite that equation. Is equals to the product. I'm going to rewrite it higher up. I'm not going to do it here because I don't have enough space. I'm going to rewrite it here. The heat of reaction is equal to the product, the coefficient times by the corresponding heat of formation minus the reactant, the coefficient, and the heat of formation. Yeah. So where is our product? This is our product. So I'm going to write it as there's a 1 there. That is 1. So the heat of formation of your product, which is that of your ethane. Write down where it is a gas phase, so you need to write that down. Okay, so that's 1. The product. You only have one product, so you are going to look at the left hand side for the reactant. Your reactant, you have C2H2. I'm assuming that is ethylene. So there's 1 in front of it. The coefficient is 1. Okay. 1, the heat of formation of ethylene, C2H2 gas phase, okay, plus 2, because there's 2 in front of hydrogen, 2 heat of formation of hydrogen gas. But we already mentioned just now, the heat of formation of any elements in its elemental form is going to be 0. So you're going to just let this become 0. Okay, so now you only have that 2 terms there left. So let's look at the heat of formation of ethane. Where is the heat of formation of ethane? That's the value. So that be 226.75. That's your product. And the reactant for ethylene, the heat of formation of ethylene. Sorry, I got it wrong. Somebody, I got it wrong. This is ethylene. This is ethane. I got it wrong. I need to undo that. Okay, I need to erase this because I'm looking at this is what? That is ethane. So this is ethane. So it should be minus 84.67. Yeah. That's your ethane minus, this is ethylene. So ethylene is here. That will be minus 226.75. So if you do the calculation, what is your final value? Is somebody should be negative something. Would be negative 300 something. Anybody calculate for me, please? I need you guys to help me with the calculation because or else you become sleepy.
Negative 311.42.
7 point, sorry,
42.
Thank you very much. Thank you very much. Okay. The rest of you guys check whether Ibrahim get it correct. Let me see. One that I have, okay, it's the same value, negative 311.42. So you don't really need to do your his. You need to do the check. If you want to check, no problem. You can use his law to double check. So you can check. Let's see. We need C2H2 on this side, on the left side. So bring this over, flip it through. Okay, so this become, I'm going to undo that. I'm going to write another equation. C2H2. I'm going playing around with his law now in order to double check whether it's going to be the same. It's equals to 2C plus hydrogen. Write down your phase. That's solid. This is gas. Okay, so this will also become negative value, 226.75. Once you flip, you change the symbol. Now it becomes negative. Okay, so now we're going to eliminate that part. So you have hydrogen gas. Hydrogen gas is on the left-hand side. So that's on the left-hand side. That's fine. You have C2H6. That should be on the right-hand side. So this is on the right-hand side. So the equation stay as it is. So let's do the sum up. You have 2C cancel on the left-hand side with the one on the right-hand side. You have hydrogen gas is 1 hydrogen gas plus another 1 hydrogen gas. That should be 2, isn't it? Why don't I have another one more? This is only, how many hydrogen gas do I have? Okay, let me see. That's 2. I don't need to play around with this third equation. Hold on. Let me undo that. I'm making you guys confused. I don't want to play around with this because it's 0. It has no significance. It's 0. So let's see. I have 3 hydrogen over here. I have 1 hydrogen over here. So that's 3 minus 1. You end up with 2. So plus 2 hydrogen. Yes. Your C2H2 should be listed down. Okay, there's no more. Cancel. No more term on the left hand side is equals to C2H6. There's no more term beside that. So you end up with your desired equation. And forget about this second equation because there's no heat of formation for it. So eliminate it. So you only have 1 and 2 actually. So you end up with this equation. So if you sum it up, you have minus 84.67 from the first equation. From the third equation, that is minus 226.75. The same thing, you will get the same value as that, as the final answer. Okay, this is for checking. You look at the equation, you sum it up, you play around with it, you multiply with the equation, the same thing you do with the heat of reaction, and you come up with your desired reaction. So that's how you get the answer. But without using his law, you can also calculate the heat of reaction by looking at this equation. That equation, you should be able to get your heat of reaction. That is for heat of formation. Right? So any questions? I'm sure you guys have come across this before. Have you guys? I know you guys already came across his method. But have you come across calculating the heat of reaction using heat of formation? Anybody? No?
No,
Right.
Doctor.
No, it's something new. Okay, let's see whether we have more examples. Okay, let's do this. Let's do this example. We have 2 examples over here. You wanted to get this equation. Sorry, you wanted to get this as your desired equation. Okay. I don't have enough space, so I'm going to bring it down. If you look at the equation just now, your heat of reaction is equal to the sum of the product, the product of the coefficient with the heat of formation minus the summation of the reactant, the coefficient with the heat of formation. So if we're going to look at that first example, your heat of reaction for that example going to be the product. You have that two products. So you have 2 in front of carbon dioxide. There's 2, your heat of formation for carbon dioxide gas. That's going to be a gas. That is one of the term on the right hand side. Plus the other term is your water. You have water, so the coefficient is 3. So 3 times by the heat of formation of water. The water form is in a liquid phase, so write it down as liquid. So that's one of your product. Okay, minus the reactant. Your reactant, there's 1 in front of the, what is that? That is methanol. So 1 heat of formation of methanol, C2H5OH, that is in a liquid phase. That is your ethanol. Plus, there's another term, you have 3 in front of your oxygen, 3 heat of formation of oxygen, and obviously oxygen will be in a gas phase. Okay, so that close down and close your bracket for the reactant. And you know the heat of formation for any element is going to be 0, so you don't have to look it up. What we need to look up is these three terms. The first one is for carbon dioxide. So we're going to look up the heat of formation of carbon dioxide, looking at appendix B1, carbon dioxide gas. Where is carbon dioxide? So, okay, it's our carbon dioxide. It's gas, so I already highlighted it here, is 393.5 minus, there's a minus sign, don't forget the minus sign. It's minus 393.5, so let's go back to that example. 2 times minus 393.5, that's the value you get just now from the appendix B1 for the heat of formation of carbon dioxide. Okay, for another, we need to look up the heat of formation of water, liquid water. So let's look at our appendix for liquid water. We did mention about this earlier, the heat of formation of liquid water. So that's water. So liquid water is here. That's negative 285.84. Okay, 285.84. Negative 285.84. That's your product. Minus the heat of formation of your ethanol liquid phase. The heat of formation of ethanol, that is ethanol liquid phase. So let's again look it up in appendix B1 for ethanol, liquid ethanol. It will be somewhere here. Let me highlight it. This is ethanol. The heat of formation for liquid phase, that's liquid. Okay, that's negative 277.63. Okay, let's remember 277.63, negative 277.63. Okay, let's do the sum. What is the heat of reaction for that reaction for the first example? Let's do the calculation, whether the answer is the same as the given solution, which is negative 1409.2. The answer should be in kilojoules per mole. Is it kilojoules per mole? No, it's not per, yeah, it's per mole of ethanol. Give me the answer, please, somebody. Should be negative, based on the look of it. Anybody going to give me an answer? Everybody very quiet. Are you guys with me?
Doctor,
Yes.
I got negative 1366.89.
1366.89.
Yeah.
Yeah. Now, anybody else getting the same value? Because I also get something like that earlier when I did it. Because I thought my calculator is at fault, so I thought maybe okay, Let's see whether you guys will get the same value as what I did. So now I'm going to do the same calculation again. I'm not sure why the answer given is wrong. Not the same. So that's plus 277.6. The rest of you guys, please do the calculation and check. Yeah, I think I got the same negative 1,366.89. Did I make any mistake, guys? Okay. This is your equation. Okay. You have two carbon dioxide. Okay, I got two over there. That's the heat of formation of carbon dioxide. I have 3 water. Okay, I got 3 there, and I got water, liquid water. I have 1 mole of ethanol. I got 1 there, and I got ethanol there. And I got 3 mole of oxygen. Okay, but oxygen, heat of formation of oxygen is 0. So by right, this is the correct calculation. After looking at it twice, I don't know why is the answer negative 1. I got a feeling that this person, the one that gave that value, must have listed this as vapor. Let's see whether that is the reason why the difference in the answer. Let's look at water. Water in a vapor phase. The formation of water. Water vapor. That is negative 241.83. Okay, 241.83. So if we substitute over here, negative 241.83, you think that will make it? No? You think? I don't think so. Isn't it?
No, doctor.
No. I don't know why the answer different. How about the rest of you guys? Did you get the same value? Negative 1366.89. I got the same value. Can anybody check what's the what mistake did we make? Or did the author give a wrong solution? Not the author. I got this somewhere else. I don't know where. Anybody? I thought I got everything right already. Right? Don't know what's the problem. Most probably the author must have got the values from somewhere else. The value, the heat of formation. I don't know why. Where is the why is it there's a difference? Okay, let's look at the second part. Let's look at the second part. This is your reaction. You're going to react sodium hydroxide with hydrogen chloride to form sodium chloride plus water, liquid. It's very important to note that the water is in a liquid phase, not in a vapor phase. We're going to do the same calculation using this equation. Right? Going to do the same using the heat of formation. So now I'm going to erase this part because I'm going to use a different equation now. And see whether when I did it earlier, I also did not get the same answer as the author. Same one as the one listed here. So let's see. We have the product, sodium chloride. So this is going to be your product. The number in front is 1. So heat of formation of sodium chloride. What state is it? It's a solid. That is very important to write down the state. Plus, you have water. Now again, you have a 1 in front of the water. Or even though it's not written, it's understood. The coefficient is 1. So that's what liquid water. Very important, liquid water, because the value, the heat of formation is not going to be the same if you're going to form vapor. Minus, I'm going to write it over here. Okay, your reactant, the heat of the number in front is 1. The heat of formation of sodium hydroxide, that's solid. Okay, plus there's another 1 there in front of hydrogen chloride, so I'm going to have enough space. Heat of formation of hydrogen chloride gas. Yeah, that's close your reactant. Now let's look up your appendix B1 for sodium chloride. Sodium chloride. Let's scroll it up. Hold on, sodium chloride. I saw it just now. Okay, that's sodium chloride. Okay. Oh, let's see. This is for what column? So that's your heat of formation. That's your heat of formation. The second column, the second column, the very last column is the one for heat of combustion. So that is for negative 411. So let's put that value. Negative 411. Right? The one in front of it. If you don't want to write that one, it's no problem. For water, liquid water just now is the same that we did just now. What did we get for liquid water just now? Can you remember? Somebody? It's 2 negative 2.84, is it? What, 5.84, is it? I'm trying to remember. Is that the value?
Yes, doctor.
Thank you. Okay. So now minus the heat of formation of sodium hydroxide. So again, we need to go to appendix B1, sodium hydroxide. Where is sodium hydroxide? Okay, that's I need a highlighter. That is sodium hydroxide. So the heat of formation. Okay, you have two values over here. We need to check. Are we looking at solid or are we looking at aqueous? Okay, the value is solid. It's written here solid, not value. It's written as solid. So we'll be looking at solid. So sodium hydroxide for solid, this is the value. Negative 426.6. So write that down. Negative 426.6. That's I'm not going to write the one in front of it. Plus the heat formation of hydrogen chloride gas. Hydrogen chloride. Hydrogen, scroll up. Let's see, where is hydrogen chloride? There's hydrogen chloride, so I'm going to highlight it. And that value is negative 92.31. Negative 92.31. So let's go back. Negative 92.31. Bracket it up and close that bracket. So what is your final value for the heat of reaction? And when I did earlier, I did not get that same value as the solution. See whether you guys also did not get the same value as what I did.
Doctor, I got negative 177.9.
Negative 177.9.
93.
90, thank you. Come on. Okay. Anybody else getting a different values? I mean, anybody else getting the same as the solution, or did you get the same negative 177.92? Anybody going to respond? Nobody? Nobody is willing?
Same answer, doctor.
Which one?
Same as doctor.
177.93.
Okay, thank you, Nabila. Negative 177.93. Okay, so I'm not sure why the values given here by on the slide is not the same as the one that we got, but I'm very sure our working steps, they are correct. I'm very sure of that because we just follow the equation, which is the summation of the product with the product of the coefficient with the heat of formation minus the summation of the reactant. That's what we did. Yeah. So let's see whether there's any more example on heat of formation. Let's see. This is from your textbook, example 941. I got the feeling that this is using the heat of formation. No, that is not heat of formation. This is heat of combustion. Sorry, guys. This is heat of combustion. There's the C. There's the C. It's combustion. So we don't have any more example on heat of formation. Yeah, so we'll be looking at heat of combustion. So let's take a break, 5-minute break for guys to ease yourself if you need to go to the loo, to the toilet. That's another way of saying it. Okay. To the WC. Yes, Ibrahim.
Can you display the QR code?
QR code. Yes, I will. Let me stop sharing this.
Thank you.
Welcome. That's QR code. How many guys? How many are you around? Let me see. Only 29. 8 of you guys are not around.
Doctor, wait, doctor. I didn't scan it.
Sorry, you cannot scan? Why? You can't see it? Is it? Is something blocking it? Can you scan now?
Can, doctor?
Thank you. Okay, guys. So for those who already scanned, if you have any other question to ask, anything regarding today's lecture or previous lectures or regarding the second test. Nobody going to ask anything. Okay, go and ease yourself, get something to drink, get something to eat. It's going to be another 1 more hour, less than that. Definitely, I'm not going to go till 4 o'clock. Okay, take a rest. Look outside instead of looking at the screen of the computer. You need to relax your eyesight. Look at something green outside. If it's raining, look at the raindrops. Okay, are you guys? How are you guys anyway? For those who still around, who did not left the computer screen, who did not left your computer, who still seated. Hey guys, welcome back. Okay, just like I mentioned earlier, you have over here 2 equations that you can use to get your heat of reaction. The first one is using the heat of formation. We have done a few examples just now. I think we got 2 examples, in fact 3 examples that we look at and how using the heat of formation. So now we'll be looking at how to calculate the heat of reaction using the heat of combustion. The subscript If you are using the heat of formation, you have a subscript of F. Oh, sorry, I'm going to highlight that. Okay, you have the subscript F if you're going to use the heat of formation. So if you're going to use the heat of combustion, you're going to have a subscript of C. And where you're going to get your heat of combustion is again from the same appendix. Okay, same appendix. So this is your heat of combustion. The last column. And the last column is going to display your heat of combustion. Okay, so you can get your heat of combustion from the last column from appendix B1. So let's go back to our notes. Again, you have the summation there, the product of your coefficient, the product of your coefficient. Let me highlight the product of your coefficient with the heat of combustion. Okay? The only difference is that from the previous heat of formation, you'll be looking at first your reactant minus by your product, which is the reverse of heat of formation. Heat of formation is product minus reactant. Okay? As I mentioned just now, method to remember is that whenever you look at heat of combustion, the fuel is the one that you're going to burn. The fuel is the one that you're going to burn, so the fuel is the one that is the reactant. So the first term will be your reactant. Okay? If you're using the heat of formation, the product is the one that is being formed. So the first term will be your product. That's how to remember. Okay, let's go back to, let's look at an example. Using the heat of combustion to calculate the heat of reaction. And let's look at this example, which is from your textbook. This is your desired equation, and you want to find the heat of reaction for that reaction. Okay, you're going to form, you're going to split ethane into ethylene. Is it ethylene? Is it ethylene? I'm not sure. I don't know if it's ethylene. Plus hydrogen. So let's use the given values of the heat of formation is already there. Okay, so now let's look at the equation. We write down the equation earlier. The heat of reaction is equal to the summation. What is the first term? Reactant or product? Anybody? Is it reactant or product?
Reactant.
Reactant. Thank you. It's going to be reactant because your fuel is the one that is going to burn. Okay, so your Sokamic coefficient, the coefficient in front of the value in front of the equation, plus the heat of combustion, the standard, the superscript, okay, minus the product, which is the product of your coefficient, and the heat of combustion. Right, so since the heat of combustion is already given in this example, so we're going to just plug in that values. So let's write down what is your reactant. Your reactant only one. So there's one in front of it. 1 multiplied by the heat of combustion for C2H6. That is actually ethane. That's your reactant. There's only one reactant. There's two products. So the first product, there's a 1 in front of it. So 1 times by the heat of combustion for C2H4. I'm surprised there's no, what phase is it? Is it liquid? Is it gas? It's not written at all in this example. Plus the heat of combustion of hydrogen. Again, you have number 1 there in front of hydrogen. So that's the heat of combustion for hydrogen. But let's look at this. You have hydrogen here. Hydrogen is an element. But your heat of combustion for hydrogen is not 0. Because we are talking about combustion, not talking about formation. Hydrogen is not being formed here. Hydrogen is being combusted here. It's going to be burned. So that is the heat of formation, not formation, combustion for hydrogen. So let me highlight that. There's a value for it. It's not 0. Okay? Let's erase that. Okay, now let's put in the values. The heat of combustion for C2H6 minus 1559.9 minus your product for C2H4 minus 1411. Yeah, you don't need to put down the value of 1 in front of it, plus the value for hydrogen, the heat of combustion for hydrogen is minus 285.84. Close your bracket. So what is the final answer? The solution in the textbook gives a value of 136.9. The unit is kilojoules per mole. See whether you can come up with the same value, 136.9. Is it 136.9? I have my textbook over here. This is example 941. Yeah, the one listed here is 1.
Yes, doctor.
Thank you. It's positive 136.9, meaning in order for this reaction, for this desired reaction to occur, you need to put in 136.9 kilojoules of heat into the reactor in order for it to react. Without putting in that amount of heat, the reaction will not occur. That's the implication of the heat of reaction. Right? Without putting in that amount of heat, the reaction will not occur. But this is occurring at 25 degrees C, 1 atm. That is the standard heat of reaction. Any questions? That example is example 941 from the textbook. We haven't looked at energy balance yet. We're just looking at heat of reaction. Because you need that heat of reaction in order to do your energy balance. Got two methods in actually how to do your energy balance. So let's see. This is also using your heat of combustion. Okay, I'm going to highlight this. This is your reaction. Is it the same as the one previously that we have covered? That's C2H6. No, it's a different. C2H6 is a different reaction. Okay, let's do this. Let's do this for this reaction. I'm going to do it over here. I'm going to immediately write the equation. Because I already have the equation here. I already have it here. So I'm going to just write down for the reactant. You have 1 in front of it. That's 1. Your heat of combustion. For C2H2 gas. Close it. There's only one reactant, so close the bracket. Minus for your product. You got another reactant. I overlooked. I'm going to erase this. There's another reactant. There's hydrogen there. Plus 2, there's a 2 in front of hydrogen. 2 heat of combustion of hydrogen gas. It's quite it could be misleading if that C in front there could be the formula for like a smaller C then. This is hydrogen gas. Right? Proceed. And you have your product, you have C2. There's 1 in front of it, C2H2. So 1 heat of combustion, more C. That it will not be confused with this C, C2H6 gas. Okay, close the bracket. So we have this now C2H26. We did got that value given here. C2H26 negative 1559.9. So that's negative 1559.9 from the previous example. Right? So that's your product. Now for your reactant, hydrogen, we did also have that value just now. That is hydrogen negative 2. That's hydrogen 285.84 negative 285.4. 2 negative 285.84. I hope I got it. See? Negative 285.84. Okay. And C2H2, sorry, the last one. the first reactant, C2H2. Let's look it up. C2H2, what is it? C2H2. That might be ethylene. Let me use a highlight. C2, I only have C2H6. I don't have C2H, I have C2H4. I don't have C2H2. What is not ethylene then? Not sure. Anyway, in that example, the value is actually given. Yeah, C2H2. Where is C2H2? Here is C2H2. Yeah, that value is negative 1299.6. So let's put that value here. Negative 1299.6. Yeah, so everything is there. So what is your heat of reaction to calculate it? Will it be the same as the one given here, negative, the value here is negative 311.38. Please do the calculation and check what is the answer. Let me also try to get the answer.
Minus 311.37, Doctor.
Sorry, what did you get? I can't hear you. Negative? Oh, sorry.
Negative 311.37.
27. Thank you very much. The unit is reduced for more. Thank you very much. Let's check the answer. Yeah, it's the same. It's just a slight difference of 337. We get 37. The answer given here is 38, but it's negative 311.37 or 38. It's about the same. That's how you do when you have the heat of combustion. Which one to choose? It's up to you. You want to heat of combustion, you want heat of conformation, unless in the test or in the final it is stated that you must use only one method, which is might be heat of formation. Then you have to use heat of formation. You cannot choose a different method. But you have a choice if it is not stated what method. You can choose either one. Heat of formation or heat of combustion. You still get the same answers. I mean, if you do both using either method, you still get the same answer. Okay, one more thing I need to point out, guys. Okay, before that, I need to point this out. This is the definition of heat of combustion. I need to point it out. This combustion, as it is implied, means that you're going to burn it with oxygen. You're going to burn it with oxygen, and you will form the usual products, which is carbon dioxide gas, water, liquid water. If there is sulfur in your fuel, then you're going to form sulfur dioxide. Of course, you're going to get nitrogen because you're going to have your source of oxygen from A. Nitrogen gas is not the product of combustion. It's just because your source of oxygen is from A, and A contains nitrogen. Okay? Another thing, if your fuel contains chloride, then it will form hydrogen chloride. But normally it's very dilute. So these are your products, more or less. I'm not saying nitrogen is the product, but these are the one that is going to be formed on the right hand side. And nitrogen, again, is not a product of combustion. Nitrogen is due to the fact that your source of oxygen comes from A. And A contains nitrogen. So that's the reason. Okay? And if you have the product, for example, your product of combustion is, for example, okay, it's just stick as that. These are your products, okay? The one that I highlighted, these are the products of of combustion. But here is one thing that I need to point out to you guys. Sometimes, just now I mentioned that your water should be in a liquid phase. The product of your combustion should be water in a liquid phase. But sometimes you can also get it in a vapor phase. Oops. It should be sometimes you get it in a vapor phase. Why is it in a vapor phase? Because the temperature is high enough for it to vaporize. Your product is being formed at a very high temperature that the liquid water evaporates into vapor. So if you have water being formed, for example, you have water over here being formed into a vapor, then what you do is this heat of reaction is not going to be the same when you form liquid water. It's not going to be the same. Now you're going to form vapor. So what you're going to do is you're going to add up this value to that heat of reaction. You're going to add up 44.01 times by N subscript W. That is the one I have highlighted here. What is NW? NW is this mole of water that is being formed divided by the mole of fuel that is being burned. For example, in this example, let me highlight it. In this example, if I'm going to form vapor, okay? If I'm going to form water vapor, I'm going to add up this value from the heat of reaction when there is liquid water being formed to this equation. So I need to calculate my NW. My NW is going to be the amount of water being formed is going to be 3. That's the mole of water being formed. And the mole of fuel that is going to be burned, that's 1. This is going to be 3. So the value is going to be 3. So I will get the sum of this whole thing, which is that my delta H, my heat of reaction is equal to minus 1366.9. Plus 44.01 times by 3. That is my heat of reaction when I form liquid, not liquid, water vapor. Not, sorry, I need to erase it. It should be produced or more. That is when, that's the heat of reaction when water vapor is being formed in the combustion process. Water vapor, not liquid. The equation over here, the one that I highlighted, the value is for liquid water being formed. So any question on that? You need to remember this equation. Guys, any questions? No question? Nobody going to ask anything? I have done the heat of combustion, getting the heat of reaction from the heat of combustion. Let's see whether I'm going to have any more examples that I can use. And now we're going to look at energy balance. Finally, we're going to look at energy balance. I'm going to give you guys the 2 methods that you're going to use. I'm going to show the whole thing in one slide. This is going to be, going to be a long way. Where is it? Wow, I think I already missed it. Okay, when you do your energy balance, as usual, you need to draw your diagram. You have to draw your diagram. Yeah. And as always, you need to do your table. You need to construct your table for the energy balance. And also, obviously, if you're going to solve for the material balance, you also need the table to calculate the amount of product being formed. Okay, so these are the few examples. Now, you have 2 methods of calculating the energy balance. Okay, now I have over here, this is the method for heat of formation method. Now, do not get confused when I say heat of formation method with the one that we just did just now using the heat of formation method. The one previously that I have covered is in order to calculate the heat of reaction. This is to solve for the energy balance. Okay, there's two things here. The heat of formation can be used to calculate your heat of reaction, and this can be used to calculate your heat, which is your energy balance. Okay, there's two methods here using the same heat of formation. Okay, so we have covered this. We're going to look at this. So the method now, to do the steps, the procedure to do your energy balance. First thing first, obviously you need to draw I did not write it here, but obviously you need to draw your diagram, draw your block diagram. Yeah, you need to draw your block diagram. Do not be fanciful. I saw a few students, I'm not sure was it this section or is it the other section, not from our section, that drew the heat exchanger, being so fanciful with the tubes inside the heat exchanger. Don't waste your time doing that. It's just a block diagram. Okay? And label everything. Label everything completely. Yeah. Get a basis. Do not forget your basis. You must have a basis every time you do the material balance. Okay, complete your material balance. You have reaction. Sometimes it's a single reaction, sometimes it's a multiple reaction. You need to do your material balance. You need to have your table for the material balance. Okay? After that, you're going to start with your energy balance. You're going to choose your reference state. Every time you do an energy balance, you must have a reference state. So if you're using the heat of formation, your reference state normally will be looking at the same, because when you use heat of formation, your reference state normally will be the elements. No, I need to highlight that, not, okay. The elements. Because you're going to form the compound from the elements, because you're using the heat of formation. So normally you will be using the elements and it will be formed at 25 degrees C and 180 amp. So your reference state will be the elements at 25 degrees C and 180 amp. If there are other components there that is not reacting in the reaction, for example, nitrogen. Nitrogen is not reacting in that reaction, then you can choose any reference state you like. It could be the inlet, it could be the outlet. It's up to you. Okay? Because that component, that non-reacting species is not involved in the reaction. So you are not restricted to 25 degrees C and 180 amp. You can choose any temperature you like. The inlet temperature, the inlet temperature, or the outlet temperature and the outlet pressure. It's up to you. Okay? So after that, you need to do of course, your enthalpy table with the inlet and the outlet. And then you will finally solve for your energy balance using this equation. This is exactly the same what we did before. We have done this. This is out, in, specific enthalpy minus in specific enthalpy, molar flow rate and specific enthalpy. It's the same as what we have done before. It's the same equation. Is equal to Q dot. If you're using the heat of formation method, the only thing you need to remember is this. Your reference state, the component that are involved in the reaction must start from the element because you're going to form it. Okay? And it should be at 25 degrees C and 180 amp. That is one method. Another method is heat of reaction. If you're going to use the heat of reaction method, that is, to me, most people prefer to use the heat of reaction method. If you're going to use the heat of reaction method, again, you need to draw your diagram, same thing, draw your diagram, the block diagram and label. Yeah. Do your material balance, have a basis, same thing. The only difference now, when you do it using the heat of reaction, your species, the product, the reactant, is going to be at 25 degrees C, 180 amp, where that value is given. Your heat of reaction must be given. That's when you use your heat of reaction method. If your heat of reaction is not given, then you have to use the heat of formation method. And normally when you use the heat of reaction, normally it will be for a single reaction. If it's a multiple reaction, then it's better to use the heat of formation method. Okay? So for any non-species, it's anything. It could be inlet or could be outlet, temperature, pressure, conditions. Okay? Same thing. The only difference from that previous heat of formation is that you have the species, not the element. Meaning, if you have methane, then you'll be using methane as the reference state, not carbon, solid, not oxygen, gas, not the elements. It must be the species, the molecule, the component that is present. That's the difference. Okay? And let's see. The equation that you're going to use is this equation. If you're going to have a single reaction, if you're going to have a multiple reaction, that's the equation. You're going to have the extent of reaction there. You need to calculate the extent of reaction. Because I mentioned just now, if you have a single reaction, it's better to use the heat of reaction, provided your heat of reaction is given. Are you guys with me? Okay. Are you guys with me? It's just, I'm talking to myself. Okay, let's look at an example then. You'll know it, you see it when you, this is heat of formation. Heat of formation, you do this equation. When you have heat of reaction, you'll be using this equation. When you have the heat of reaction, you'll be using that equation. The difference is that you have this term here. That's the additional term. Yeah? So let's see if there are any example that I can look at using the heat of reaction. And let's look at example 951. And this is one example from the textbook. Fortunately for this example, you have the outputs already. The amount of product is already known. You don't need to calculate you don't need to do the material balance. This example is just used to show you how to do the energy balance. Yeah, you don't have to do the material balance. Okay, here you have 100 mole of ammonia coming in at a temperature of 25. Beside ammonia, you have oxygen also coming in. Okay? So your ammonia is going to react with the oxygen to form nitric oxide, water, and oxygen. Is there any oxygen? No. The oxygen coming out is because there is excess oxygen. There is no oxygen in the equation of your product of your reaction. Okay? The reason the oxygen is coming out as the product because you have excess oxygen being fed in the feed. Okay? So the question asks for what is the heat transfer into the reactor or out from the reactor. The reaction occur the reaction occur at 300, so your product exited at 300 degrees C. So you already have the material balance. Your heat of reaction is given. So since you know that your heat of reaction is given, automatically you're going to use the heat of reaction method. And the equation for the heat of reaction method is, I'm going to write that equation. Q dot equals to your change in enthalpy is going to be your extent of reaction times by the heat of reaction. This is the reason why you need to calculate your heat of reaction. We have done a few examples earlier at the very beginning of the lecture. This is the reason why you need to have your heat of reaction. For this case, it is given. But if it's not given, you can calculate it, okay, using the heat of formation or the heat of combustion method. Plus out for molar flow rate, the specific enthalpy, this is the same as the previous chapter 8, in the specific your molar flow rate and your specific enthalpy. The only new term is the one over here, the additional term. Okay? So now let's do our table. How many components do we have? 1, 2, 3, 4. 4 components. I need 4 rows. More. Okay. This is my component. In, out, Ouch, ouch, that's terrible. Okay, let erase. Let me erase partially. Okay, this is, let's see, what do I have? Ammonia. I have ammonia. I have oxygen. I have nitric oxide. I have water. That's the that's the component that I have N in. What's the unit? Mole per second. My enthalpy, mole per second. Oops, I forgot to write in. In kilojoules, not mole per second. Kilojoules per mole. In and out, that's mole per second. And my enthalpy out, kilojoules per mole. Okay, done. Okay, we know the flow coming in is given already in the diagram. You don't need to draw the diagram, it's already there. So we have 100 mole per second coming in for ammonia. Let's me undo that. Okay, that's 100. 200 for oxygen. There is no nitric oxide, there is no water coming in. What phase is the water? It's not stated. Okay, it's gas. It's gas. From this equation, it's gas. Okay, since your amount coming out, you have nitrogen oxide 100. You have water 150 given in the diagram, and your oxygen is 75. There is no ammonia at all in your product, so that's none. So now we need to find the enthalpy, H1, H2, H3, H4, H5. Your reference state, we're going to use the method of reaction. So we're going to have the reference state as the component that are involved, that are in the reaction and not in the reaction. Or both of them should be listed as the component. So that is, what is it from the equation is gas. So I'm going to write gas, comma, I'm going to write it as the whole thing. The oxygen gas, nitric oxide gas, and lastly you have your water gas at 25 degrees C, because this is reacting at 25 degrees C, and 1 atm. So that's your reference state. Your basis, obviously you need to write, even though you don't have to draw the diagram. Let's say 100 mole per second of ammonia. Right. That's your basis. Okay. So now we need to calculate the enthalpy. Where are we going to find the values for the enthalpies, guys? Do you have any table to look up? Anybody?
Maybe CP or table B8.
B8. Okay, B8. We have oxygen, we have water vapor. So let's look at table B8. Okay. Thank you. For your second test, do not use table B8. It has been specified that you do not use table B8. But in this example, you can use B8. Test B5. Okay, I'm coming. Okay, that's B8. And let me tidy it up. Okay. So what component did we have just now? We have water. We have water. There is water here. We also have oxygen. Okay. The temperature. Let me look at the temperature again. We have a temperature of 25 degrees C here. When your reference state is at 25 degrees C, so what do you think is the enthalpy of your inlet component? The enthalpy of your component at inlet?
0, Doctor.
0. So this is going to be 0. That is going to be 0. Because it's the same as your reference state. Right? And I'm assuming that this is also at 1 atm. This is also at 1 atm. Right? You have the outlet at 300 degrees C. So we're going to look at the temperature of 300 degrees C for oxygen and water vapor. The rest I don't think is available in the appendix B8. For 300 degrees C, let me highlight 300 degrees C. For oxygen, that's the value. For water vapor, this is the value. Right, so for oxygen, 8.47. And let's write that down. For oxygen, 8.47 kilojoules per mole. And for your water vapor, let's go back again to that appendix, is 9.57. Okay, now for the other, the only enthalpy that we need to calculate is for nitrogen oxide. We need to look at appendix B2. We need to use the polynomial equation. So look at appendix B2 for nitrogen oxide. It's falling up if we reach B2. Before, you can look up in your textbook where actually is nitrogen oxide. Nitric oxide, not nitrogen oxide. This is nitric oxide. I saw it now. This is nitric oxide. Nitric oxide, we're going to use degree C. It's a gas, form 1. So these are your A, your B, your C, and your D. Okay, now I'm going to do this here because I'm going to click back and forth. It will be difficult for me. So my CP, I'm going to integrate my CP from 25 degrees C, that's your reference temperature just now, to 300 degrees C, that's the temperature of the product, and that's the CP of nitric oxide, which is in a gas form with respect to temperature. So we're going to do the integration from 25 degrees C to 300 degrees C because over here it's stated as degrees C, so it will be degrees C. Remember that because I saw one student using the Kelvin and then putting down the temperature in degrees C. That's a very major mistake. It's 3 plus 0.8188 times 10 to the power of minus 5 T minus 0.2925 times 10 to the power of negative 8 T square, and lastly plus 0.3652 times 10 to the power minus 12 T to the power of 3 dt. Just make it. Okay, so if you do the integration, what will be the enthalpy, please? This is the enthalpy that we need for enthalpy 4. I will do also the calculation. 9.5 times 0.81 to the power of negative 5 minus 0.2925 to the power of negative 8. Oh, I forgot the x. That minus 0.2925 power negative 8 alpha square plus 0.3652 to the power negative 12 alpha x to the power of 3 comma 25 comma 300. Those, see what you get the same as me? You get the same value? Anybody?
Yes, doctor.
Thank you. 8.453. So we're going to go back to the example. 8.453. So we have completed the table. So now we need to find the extent of reaction. What do you think is the extent of reaction? The formula for the extent of reaction is equals to mole consumed or produced, normally consumed, per the coefficient, the coefficient of that component. So if we look at the reaction, you have two components here. You have ammonia and oxygen. Let me erase this properly. Okay. Oh dear. Okay, you have these two components, ammonia and oxygen. So you know from this table, your ammonia coming in is 100. Your ammonia coming in is 100. There's no ammonia left in the product. So what do you think is the amount of ammonia being consumed? Anybody? 100. And what is the coefficient of ammonia in this equation?
-4.
Don't put negative there because we're just going to look at the number. Sorry.
Oh.
Yes. Okay. If you have negative when you do the meter balance, when you calculate the external reaction, no negative sign. That will be 25 mole per second. Okay. So that's going to be 25. So let me 951. I'm going to double check with the textbook. Example 951. See whether the external reaction is the same as what we got. Yeah, it's the same. So now we're going to complete the equation. We have the energy balance, the H, change of enthalpy, change of kinetic energy. You still need to complete this full equation. Do not leave it out. Is equal to your heat plus your shaft work. This is going to be 0, no working parts. Your potential energy, no change in elevation or height. Your kinetic energy, no change in velocity or no acceleration. So you end up with your Q, which is your heat supply or release, is going to be the change in enthalpy. And that is going to be the same equation I have got over here. Right? That's the same equation. So I'm going to write it all over again. Your extent of reaction, your heat of reaction, plus out, this is from chapter 8, minus in your product of your flow rate and your specific enthalpy. So your external reaction just now we got already is 25 mole per second. And that is your external reaction. Your heat of reaction is given. That is your heat of reaction minus 904.7. Or minus 904.7. The unit is kilojoules per mole. So you will cancel that out. You have kilojoules per second. Now you do the from the table that we have constructed. Fill out this part of the equation. We have 75. I'm not going to write down the unit because we know what the unit is going to be. 8.47. That is for that row. That plus 100. 8.453 plus 150 times 9.57. I'm not sure I have enough space. Okay. Oh dear, I don't have enough space. Ouch. Sorry about that, guys. Now, we need to do something here. Oh dear, let me erase this. Yeah. Let me undo that so that I can fit everything in. Let's look at the table again. Ouch. Why am I doing this? I don't have enough space now. Somebody please do it manually for yourself. I don't know how to undo this. What to do? Let me write. Okay, there you go. 75 times 8.47. I'm trying to fit everything in. That's 100. 8.453 plus 150. 9.57. Okay, done. That's nice. That's for the product. Minus your reactor. That's for the outlet. Now inlet is going to time by 0 because your reference state is at 25. So that's 100 times by 0 plus 200 times by 0. Okay, now do the calculation, please. So what is your answer? should be in kilojoules per second. So let me do that too. 25 times negative 904.7. That is going to give me minus 22,617.5. That's that part. Okay. And plus the bracket 25. That's going to be 2,916.05 minus 0. So what is your final answer? Minus 22, sorry, 22,617.5 minus negative 20,701.45. Did you get that? Kilojoules per second. Let's see the answer. 50,700. I got, that's good enough. Did anybody get a different value? Anybody? Did you get a different value? Still on the way, calculating. I saw the answer from the solution is negative 19,700 kilowatt. You got, that's about it. I think the textbook round it off. That's negative because heat is being released. This again. Anybody get a different value? Are you guys with me?
Same.
Thank you. This is how you do your energy balance. What's the difference before without reaction and after reaction? The difference is only using this part, or if I highlight it, this part. Oops, I erased that. This part. That's the part that is different if you have reaction. The one previously we have done without reaction is just out minus in. Now we have this term, which is the extent of reaction and the heat of reaction. That's why you need to calculate the heat of reaction. You have three methods to calculate the heat of reaction. You have the His rule or His law, then the heat of formation and the heat of combustion method. So you need to know how to calculate your heat of reaction over here. Right, so if you have the heat of reaction given, or you can calculate it, you can calculate it, then you use this method, which is the heat of reaction method. Any questions? I need to point out, your reference state must be looking at not the element, at the species. What all the species that is in the reaction and that is not in the reaction should be at 25 degrees C and 1 atm. You cannot choose any other reference state. You have to if you're going to use the heat of reaction method. Okay, guys? Any questions? Anybody? You have about, the time now is 3:46, roughly 5 minutes for Q&A. Anybody? It's very important that you know this. This is definitely going to come out in the third test and it's going to come out in the final. I should be giving you guys your third assignment soon. Once you know how to do this energy balance, your third assignment is on the way. Any questions? Am I alone? Anybody? Any question? How many participants do I still have left? Okay, I still have 28. Somebody left. Somebody left. So, anybody? Any questions? No questions?
No, doctor.
Good. I would like it if you have anything that you need to raise, because when I give my lecture and when I look at the test, it doesn't reflect. It's you understand during the lecture, but during the test, you guys cannot do it. Yeah, it doesn't reflect. I would prefer if you have anything to ask, please ask. Yeah. I really would like you guys to perform well, because I thought, since you understand the lecture, then you should be able to do the test. Okay, guys, if you don't have any other questions, then we will see each other next week on Sunday. We're not going to have a holiday. Johor doesn't celebrate New Year. Even though you are in KL, even though you are in Selangor, but since UTM is in JB, so we're going to have class on Sunday at 15 a.m. next week. Okay, guys, thank you very much for attending, and do take care, because nowadays the COVID-19 seems to be getting out of control. I mean, the numbers seems to be getting larger and larger. So just take care of yourself, play safe, and see you guys next week. I mean, online next week. Hey guys, Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Doctor.
Welcome.
Thank you, Doctor.
Welcome. Oh, somebody say it's more per hour. It's more per hour. The question is which question? Oh, the question says more per hour. I got my diagram more per second. Okay. So please correct the unit.